Hi, so this last topic is really the meat of this lesson for this Saturday, October 12th. It's recursive functions, and recursive is kind of a fancy word for functions that kind of use the prior entry. They use an earlier output value to figure out the next value. It's something that you probably do a lot intuitively without really thinking about it, but it does have a name, recursive. This is also a big concept in computer programming. Um, Functions that call themselves is another way to think about it. There are some sort of very famous problems. It's a big concept in computer science, recursion. But at any rate, the piece that we're looking at here, we're really interested in the idea of these functions that do something with the prior value. And we need this idea of what happens with this notation. Okay, so, all right. Actually notice that I guess I technically have a little error here because where this f is, it should really also say asada. So I really should have written it like this. And I did that on all of them, but I'm not going to change it now. I think we can still figure it out. Okay, so what is this thing saying? Well, this may be like scary looking, but the idea here is I've got a brace that gives me a choice. So when x is 0, so when my input value is 0. So again, I've just got a machine here called asada of x. Let me cross this out so this doesn't confuse us. Okay. So I've just got a machine here called asada of x. What does this machine do? Well, it's a bit less clear than our formula for crunch. I mean, crunch, we're pretty familiar with this from like other things we've seen in algebra. We're probably less familiar with this bracket type notation. So remember, this said first add 4, then multiply by 2, then add 10. Okay. So what is asada of x here telling us? What is this going to do? Well, it says that if I dump a 0 in, it's 10. So that's all that says. When x is 0, it gives me 10. Now, the second part is maybe confusing looking. We're going to follow this idea of what we did with that Simon function, where we added or subtracted something to the domain value before we put it in the function. But the idea is here, well, okay, if I put a 1 into this, I'm going to end up with, well, 1 minus 1 is 0. So I'm going to actually end up with asada of 0 plus 3. Well, what's asada of 0? It's 10. I mean, I can just look it up right here. Asada of 0, when I put 0 into this, I get 10. So if this thing then is 10, this must be 10 plus 3, which is 13. Okay, so really what this thing is saying, this is a very sophisticated way of really saying, and I guess we'll do one more, but it's really saying, like, take the last entry and add 3. This is what this says. This minus 1 effectively says, get the last one, now add 3 to it when x is bigger than 0. So let's try this next one. So if asada, if I'm putting a 2 into this machine, asada. So asada of 2. Well, that's going to give me a 2 minus 1, right? Which is going to give me a 1 in there. Well, what did I say my value was when I put a 1 in there? It's 13. Well, okay. 13 plus 3 is 16. So there we go. And that gives me that. So just kind of intuitively, if this always says I take the last thing and add 3, so I'm going to take my last thing and simply add 3. So in this case, to get this one, I'm going to go to my prior entry. So if I'm on 3, my last entry minus 1, I mean my entry minus 1 is the second entry. So 16 plus 3 is 19. And then 19 plus 3, 19, 20, 21, 22. Right? Okay, now, so if my entries are, now it's asking me to make to say some other things here. So, So my entries are 10, 13, 16, 19, 22. My directions say circle linear or non-linear. If the function is linear, write an explicit rule. Okay. It is linear, right? I mean, my differences here, we kind of talked about that last time. 13 minus 10 is 3, 16 minus 13 is 3, 19 minus 16 is 3, 22 minus 19 is 3. So every single time I've got a constant difference, which we learned that from all our y equals mx plus b experience. If I go up by the same amount every time, and I'm talking addition and subtraction, right? Then we're talking about a linear function. When they want me to write an explicit formula, really what they're saying is, can you convert this recursive form, this form where it I'm looking at the prior entry to find the next entry. I can write that in what's called explicit form, which is going to be the more standard form that you're used to. So since it's linear, you can use your little friend y equals mx plus b, that's your good pal. In this case, this is easy because it gives us a y-intercept, so I know right away that this b value has to be 10. The slope of this, since it goes up by 3 every single time, is 3. And so that's what this thing would look like. And you can try it. So does this work? So if I put a 2 in there, I should get a 16. So 3 times 2 is 6. Plus 10 is 16, so it does work. So this is my explicit formula. So another way to write this thing, asada of x equals 3x plus 10. So this form is called explicit, where no matter where I put the domain value in, if somebody gives me a domain value of 100, I can plug it in there for the 3. I have a rule that I can follow step by step, just like crunch. It says times 3 plus 10, and it gives me an output value. Versus this recursive form, which says, in a very fancy way, hey, start my table off at 0. When my domain value is 0, I'm going to start at 7, and then take my prior entry and take away 2. So in this one, looking here at this Hennessy's function, it really says I'm going to start with 7, I'm going to take my prior entry and take away 2, and like more informally, and you do this all the time when you're doing these, I'm sure, you say, oh yes, this goes down by 2 every time, and I take my last table entry and I take away 2. So if the thing is linear, if you find it's linear, circle linear, write an explicit function for it. So that's what's going on there. I don't think I'm going to be able to go through this whole thing. I think this video is getting kind of long. I'll make one more mention of like what's going on here, and hopefully you'll be in class and we can kind of do the rest of this in class. But so for the words, we've got at Fernandez Dazzle Glitter Fashion Belts, a blank belt costs $20. Each design is $5. So we want to convert these words into a recursive function and into an explicit function. So this is kind of extending, I think, the stuff you've seen in school would be my guess. Well, a blank belt, I mean, well, what are these domain values? These would be my the x, the thing that goes into this cost function is going to be my number of designs I order, right? If I order more designs, the cost is going to go up. So here, when I order 0, the thing costs 20. That's what this means. A blank belt is 20. So when I order no designs, it's 20. So that's just 20 bucks when x is 0. Okay, now when I'm bigger than 0, so think about like what this thing is doing. It's every time I add a design, right? Isn't this what this is saying? It's going up 5 bucks. So how do I write this in this fancy recursive form? Well, you're basically saying take your last thing. So take your guy prior and add 5. Because wherever it is that I am on this guy, on this belt, I could have ordered 500 designs, I could order 1 or none. But wherever I am, if I add 1 more, I'm going to add 5. And how am I going to figure that out? I'm going to take whatever cost I'm at and add 5 to it when I add 1 more design. And that's the way of saying that in the recursive style. Now, if I want to say this in the explicit form, well, this thing is linear because this is just simply a plus or minus 5. It's going up 5 every time. If I made a table, you'd see a constant difference of 5 every time, so it's definitely linear. So how can I write this? I can say, all right, well, I start at 20 bucks. And my slope on this guy, if I go up 5 every time, has to be 5. So that's the form that you're more familiar with. And this is your number of designs. And this gives me my cost. So hopefully that gives you a pretty good idea of how to do it. I left out in this video the kind of new stuff where we're headed with these recursive functions, where now we've got these percent increase decreases, and that's why we really did work on this stuff with the factor, and this is heading us toward some super cool stuff we're going to be doing with the exponential. But it's a kind of interesting way to look at this, and I think it's an important and interesting thing to expose you to, and I think you can do it though too. So, all right.